Hello everyone, welcome to this segment of Mr. McCarthy's Flipped Classroom. Thank you for participating and for investing in your own education. By watching these videos from home, you're allowing us to have more constructive, viable time in class and ultimately get more done. As always, there will be a short quiz tomorrow about the content of this video. Please take notes as the quiz will be open note. Watch out for the weird fact thrown in there somewhere. That'll be worth extra credit. Today I'll be introducing trigonometric functions. People get really scared of these, but once you get them, they're a piece of cake. The first question that you are probably asking is, what is a trig function? In short, trigonometric functions help us understand the relationships between the angles of a triangle and the lengths of its sides. As we have said before, functions should be thought of as machines. You put in something, and another something comes out. In this case, you put in the measure of an angle. What comes out is generally a fraction that can help us learn what the sides are. Okay, Mr. McCarthy, but why do I need trig functions? Well, Jimmy, the answer is simple. They're essential in learning more about triangles, the basic shape in math that helps us understand geometry and eventually calculus. Think of trig functions as your introduction to higher order mathematics. Now for the follow-up question. Is this skill practical in real life? The answer, Jimmy, is no, not really. Most jobs aren't in engineering, design, mathematics, or architecture will never use trigonometric functions. However, they encourage a stepwise thought process that is invaluable for almost any career. Everybody needs employees that attack problems in logical steps, and they're willing to pay lots of money to do it. That being said, let's get to it. Our three basic trig functions, the trig trinity as they were, are sine, cosine, and tangent. In this video, we will learn how to use sine and cosine. We will attack tangent in class tomorrow. Given one angle and one side, we can figure out the rest of the triangle using these functions. For this video and for class tomorrow, you'll need to reference your unit circle, so have that on hand. If you don't have it, or can't remember what it means, please pause this video and pull up my video from a few days ago on unit circles. If you don't have an understanding of that, we can't move forward. If we have one side of the triangle and an angle theta, which is signified by that strange circle-looking thing with a line through it, we can apply our trig trinity to find the lengths of the other sides. If we plug in the angle into our sine function, it will spit out a fraction. That fraction will equal the length of the opposite side over the length of the hypotenuse. Let me repeat that. The angle produced by the sine function of the angle theta will be a fraction that equals the length of the opposite side over the length of the hypotenuse. The opposite side is the side of the triangle opposite the angle. Look at the triangle diagram to see it. The hypotenuse is the longest side, and the non-hypotenuse side that is next to the angle theta is called the adjacent side. The cosine of theta will produce a fraction that is equal to the adjacent side divided by the hypotenuse. The tangent of theta will produce a fraction that is equal to the opposite side divided by the adjacent side. This has led math people to create an easy to remember acronym, SOHCAHTOA. The S stands for sine, the C stands for cosine, and the T stands for tangent. O stands for opposite, A stands for adjacent, and H stands for hypotenuse. SOHCAHTOA. So, sine is opposite over hypotenuse. So, cosine is adjacent over hypotenuse, ka. Tangent is opposite over adjacent, toa. If you remember that, you'll be in great shape. The problem is we can't use degrees for this. It just doesn't work. We first need to convert our degrees into radians. We worked on this all last week, so you should have it in your brains. If you don't, pull up videos from last week to remind yourself. Here's our fun fact for the lesson. I know you're waiting for it. The radian was first used as a concept in 1714, relatively late in the grand scheme of mathematics. That concept didn't have a name until 1873, when James Thomson used the term in print in England. Maybe this wasn't such a fun fact, but I'm a major history nerd. So, here's our problem. We have A, which we don't know, B, which we know is 3, and C, the hypotenuse, which we also don't know. We also have an angle 30, which we're going to use as our theta. In order to convert degrees to radians, we need to multiply by pi, and then divide by 180. In this case, our angle is 30. Do that on your own right now. You can just watch me do it, but you want to learn this stuff, right? Go ahead. Work on it. Are you working on it? Okay. Great. Let's move on. When we multiply 30 by pi and divide by 180, we can get rid of the 30 and reduce the 180, and are left with pi over 6. Got it? Good. Let's move on. We see that now we have an angle in radians and an opposite side, but nothing else. This is not a problem. According to SOHCAHTOA, we can work that out anyway. According to our unit circle, the sine of pi over 6 is 1/2. We also know that the sine is equal to the length of the opposite side over the length of the hypotenuse. Since the sine of pi over 6 is 1/2, we know that 1/2 must equal 3 over the length of the hypotenuse, which is labeled c. Using basic algebra, we know that c must equal 6. If c is 6, then you can figure out the adjacent side, labeled a, using cosine. According to the unit circle, the cosine of pi over 6 is equal to the square root of 3 over 2. Don't be scared. And more importantly, don't try to figure out what the square root of 3 is. It'll just waste your time. We're going to leave things in terms of square roots anyway. So, if the cosine of pi over 6 is equal to the square root of 3 over 2, and the cosine is equal to the adjacent side over the hypotenuse, remember SOHCAHTOA, then the square root of 3 over 2 must equal the length of side A over 6. You following? Using algebra, we move things around and learn that A must equal 3 times the square root of 3. Again, not scary. So this is what we have. Isn't it pretty? I think so. Then again, I'm also a math teacher. That being said, we have to check it. The best tool for checking this particular right triangle is the Pythagorean theorem. This only works for right triangles. Don't forget that. By setting these up, we square 3 square root of 3 as well as 3. 3 square root of 3 squared is equal to 9 times 3, which is 27. 3 squared is 9. 9 plus 27 is 36. The square root of 36 is plus or minus 6. Since the length has to be positive, this is positive 6. But would you look at that? The sides fit with one another. Magic? Maybe. Astounding? Definitely. Math? Absolutely. So this is where we came from, and this is where we went. Pretty cool, at least to me. In class, we're going to work with these concepts, manipulate them, and hopefully become masters. I hope that if you didn't get something from this, you can go through it again and try to get familiar with it. We'll go over these tomorrow. See you tomorrow, and look out for the open note quiz. Thanks for watching, and have a great night.